Good morning, everyone. I'm sorry to switch the language to English. So in this presentation, I'll try to give you a flavor of the field in which I work rather than delve into the details of results and stuff. So I'll give you an overview of our research field and why we think it's important to study this. So I'll present on this broader topic of solar storms, what are solar storms and how they affect our near-Earth space and can even affect our daily lives. I'll start with a very brief introduction of myself with like a map of Europe and my journey that led me to Finland. I grew up in southern France until I moved to Paris for my university studies. So I did like typical bachelor, master, PhD studies in Paris, already in space physics, so I'm studying the solar storms. Then I moved further northward to the Netherlands. I worked for 2.5 years at the European Space Agency before finally arriving in Finland in 2017 at the University of Helsinki in the same research group where I'm now. And now I'll move to research, and at the center of our research, one of the main actors is the sun. And here's a picture of the sun today. We can't see it from Finland, but we have a spacecraft that can actually observe it from space. And if you look at the sun in visible light, so as if you looked at it with your own eyes, which I recommend not to do if you don't have proper filter glasses, it's quite boring. It's like just this white ball with sometimes some dark spot. There's one today, and that's basically all you can see in visible light. But the sun can become much more interesting if you look at it in non-visible light, and in particular in ultraviolet light, where you can start seeing like hotter things that happen at the sun. And instead of just this white ball, we see much more smaller structures that are actually very big on the sun surface, with these loops here above the sun surface. I can play the video once more. And these structures are really big. So you have this very small dot at the center showing the Earth to scale. So this loop on the sun are really giant. And everything moves, as you can see in this video. Everything's changing all the time. So it's far from being a boring place. And among all this like twisting and structure that we see there are times when some of the structure erupt on the sun. And this is an example of one of these. So we had seen this, I had mentioned these dark spots on the sun surface, and these are linked with particularly big loops on the sun surface. And from this region that we call active regions, because things move and happen in there, that's where the solar storms are born. So what is a solar storm? A solar storm is a big eruption of solar matter that is ejected into space. And that's what you see on the video in there. You see this like bright material going into space. Some of it falls back on the sun surface, but most of it leaves into our solar system. And this is charged particles coming from the sun. And when we talk about charged particles, we also have electromagnetic fields playing an important role, which makes the physics of the structure both very complicated and very interesting. And we can track these solar storms as they move further into the solar system by not only looking at the sun surface, but what is going on outside. So these are pictures, like a combination of pictures from 3 different instruments. The green one at the center look at the sun, and then we have the blue one and the red one that look further and further out from the sun by hiding the sun in the center so that you can see fainter structure around it. And here on this video, what you see is a solar storm that left from the top left corner of the sun. And you see that it's coming again now, this bright structure, sort of giant bubble that expands into space. And they travel further and further in the solar system. In that case, it didn't go towards Earth because we are like filming the sun from here, and it went in this direction. But there's cases where the solar storms are heading towards Earth. And so that's an artist view this time of one of the solar storms traveling towards our Earth. They can also interact with the other planets in our solar system. But today I'm going to focus on Earth because that's the environment I'm working on, and also what we are working on in our research group at the University of Helsinki. And what happens when these solar storms arrive at Earth is particularly like there's a complicated interaction because the Earth is not just sitting there and with the solar storm arriving at it, but the Earth acts as the Earth has a sort of giant magnet that is going to protect us from the solar storm. You know that the Earth has a magnetic pole, north and south. That's what we use for compasses to know where the north is. But this magnetic field that we measure on the the Earth's surface also expands in space around us. And we sort of display this field as these white lines that show the force of the Earth's magnetic field around us. And it's what we call a dipole mostly, so with the field lines going from the South Pole to the North Pole. But because we have so not only the solar storms, but also a solar wind, so a stream of particles coming from the storm in which the solar storms are sort of stronger gusts in the wind, this dipole field has a sort of distorted shape. So in the front, on the picture at the bottom, you see that the shape of the field of the Earth is pushed towards our planet because that's the side that takes the wind head front and the storms when they're coming. And then on the other side, we've got this extended, we call that the tail because it trails behind our planet and extend actually very far into space. And this magnetic field will act as a natural shield that will deflect most of the solar storm from us. But this shield is not perfect, and the solar storms can open a breach in this field, as we'll see in this video. So again, the lines show the magnetic field. On the left, it's the magnetic field coming from the solar storm. And you see that when it's oppositely directed with the Earth magnetic field, it cancels the Earth magnetic field. We call this process reconnection. The field lines open in front and are then taken towards the other side of the Earth. And I wait for the movie to play again so that we can see what is going on in more detail. We see again this reconnection going on. So in the front of the Earth, this opens our magnetic shield, but also, as you can see, the green lines that are now open are going to accumulate on the tail of the Earth. And there's another cutting of those field lines that happens there. It's again a reconnection, and this launches particles very fast into the Earth's atmosphere. And this is what creates the aurora, the northern lights that you can probably see very often in northern Finland. So I don't know, most of you have probably seen auroras. Yeah, I still haven't seen them, even though I work on those. I should go to Lapland at some point. And, but yeah, Finland is a great place to watch the aurora. So what happens, we have these particles coming from the tail, and they're going to hit particles in our atmosphere. And in particular, they're going to hit oxygen atoms there. And the green light that makes most of the aurora is actually due to oxygen atoms that are excited by the particles coming from the tail and re-emit some light to come back to a quiet state. And each of the different colors of the aurora correspond to a certain atom in our atmosphere being excited. So the green color is the most common. Then you have red in some cases. That's to also oxygen, but another state of oxygen that depends on the energy that is received. There's also blue light that is sometimes observed in the aurora. And I couldn't resist to put you some nice picture of aurora. It's really the nice side, let's say, of looking at solar storms. It's this consequence of them, the aurora. And we see very, very different shapes of this aurora, many different colors. And this is, these shapes are related to the magnetic field configuration in the tail of the Earth, and that makes this very complicated structure. And if you're curious about the aurora, there's a book, Reventuri Bongaren Opas, that was released 2 years ago now, I think 2018, by Minna Parmot and other authors. So Minna is our group leader in the space physics group at the University of Helsinki, and she presents the book as a mushroom guide for aurora. So you have all different shapes and colors of auroras, and with the idea of identify them, try to find them if you go aurora hunting. And it also has a part about the science in aurora and how they're formed and so on. And so as I said earlier, the aurora is really the nice effect of solar storms. You really want a solar storm to happen if you're out there chasing for auroras. But the solar storms can also have very nasty consequences for human technologies, in particular in space, but also on the ground. And here's a schematic, which is probably too small for you to read what's written on there, but it gives you an idea of how many different effects that the solar storms can affect in many different ways. Just to name a few of those consequences, in particular, solar storms can disrupt GPS communications and satellite communications in general, which can be very damaging in our society when we all have our cell phones and rely on GPS to go from point A to point B. It can also be dangerous for astronauts in space if they're outside the space station, but we can also imagine later when there's going to be space travel to the moon or Mars that these solar storms are going to become a big problem, because the particles that are in the solar storms can create radiation, just like a nuclear explosion next to you would create, which is, again, not really recommended to be standing next to. And then there's also possible effects on the ground, and the worst of them are large electric currents that are induced in large structures such as railways or pipelines or power grids. There's been some very strong storm. The strongest one that took place in 1989 caused a power failure for 9 hours in Quebec. So they can really have devastating effects, the strongest storms. That can then take a long time to recover because you need to fix the transformers that have been destroyed by the storm and so on. So now let's go more to a bit to the science. How do we study those solar storms? And in our field, the main tools are spacecraft observation and theory, but theory is mostly numerical simulation. So you don't just solve equations with pen and paper, you rely on a computer model to solve equations. And here are two examples of those tools, those I use in my everyday research. On the left, you have an artist view of the cluster mission. It's a mission launched by the European Space Agency in 2000 that is still orbiting Earth, and it's made of 4 identical spacecraft that measure particles and electromagnetic fields in space around Earth. And 4 spacecraft are flying information in this mission to give us information about structures in 3 dimensions, and so that we can know whether what we observe at one point in space is something passing by the spacecraft or something that just appeared and is going to disappear when the next spacecraft come, because they're flying next to each other. And then the other main tool that I use is the Lucile computer model. So it's massive supercomputer simulation that is being developed at the University of Helsinki in our team. And it gives us a very unprecedented view of what's going on in near-Earth space, because it has both a description of large and small-scale processes in the code. That makes it very heavy to run computationally, so we use extensively the facility of the CSC in Finland and also outside in Europe. But then we can go to very detailed physics with this model. And more specifically, which parts of near-Earth space I'm interested in my research. Lately, I've been working a lot on a region that we call the Foreshock. And the Foreshock is, I just come back to the previous picture, this extended region here to the right with all the waves that you see extended in space. The Earth is the small blue dot in the dark blue region. And the dark blue region around it is the Earth magnetic field, so the magnetic shield of our planet. But then in front of that, we still have some structures that are part of near-Earth space. And this is actually a shock wave that slows down the solar wind. So the Earth is sitting in the wind just like a stone in a river, and that forms this sort of arc in front of it, just like the stone would change the current of water around it. And in my research, I'm really interested in this outer region, so where we have all these different waves. So that's the way, called the Foreshock, and we see it in our simulation. Here it's shown by these wiggly lines on the right, or this sort of ripples in an artist view of a solar storm coming. And what I was working on recently is how the waves that we see in this region change when a solar storm comes. And the answer is they change a lot. And the left panel here shows the waves in a quiet solar wind and quiet conditions. So we have this nicely structured waves. And then on the right, you see what happens in the middle of a solar storm, and things become much more complicated. The bottom panels show the same conditions, so quiet and solar storm, but observed by the cluster spacecraft I mentioned earlier. And we see again the waves changing from something very simple to something much more complicated. And one way to get a better idea, rather than those plots that are very obscure when you're not used to looking at this kind of data. One way to think about the changes that we see here is to think in terms of sounds. What we see in the change of the waves is a change in frequency going from a given frequency to twice the frequency. If you think in terms of sound waves that we can listen to, it's actually changing from a given note to 1 octave higher, if you could hear the Foreshock. And also, we see much more complex waves, like not just one frequency at a time, but many different frequencies. So if you sang the Foreshock, if you hummed the Foreshock, you would get like a lower note first, like and then you would go 1 octave higher, but with more of a tremolo sound. That would be your Foreshock during a solar storm. And a colleague of mine turned the waves into audible signal that do not sound like singing. And I'll try to get the sound to work here. So that's the solar storm with the high note and the complex frequencies. And then if the video loops, no, again, it doesn't loop, we'll hear the, so that's the low note of the quiet conditions. And that leads me to my conclusion. So, well, solar storms, they create these beautiful auroral displays that we are sometimes lucky enough to see in the sky, but they also have very adverse effects on technologies in space and on the ground. So it's interesting to study them both for physical understanding of what's going on, and also to be able to forecast the effects of those storms, forecast what we call space weather. So just like we try to forecast atmospheric weather, is it going to rain or not tomorrow? We're trying to be able to forecast the condition in space. Will there be a storm? How strong will it be? When will it come? And so on. And we use spacecraft measurements, computer models to try to better understand this, and hopefully being able to have accurate forecasts at some point. Thank you for your attention.